Hi everyone, we're going to talk about inferential statistics today. Background might look a little different. I'm actually traveling as I'm recording this, so what you see is not my office or my office at home, but the hotel room. At any rate, let me just give you the agenda for today. We're going to talk about hypothesis testing, and then we're going to talk about how to pick the right statistical test, and that's really in preparation for the exercise for next week. So the group of sort of statistical tests that we're talking about today is really inferential statistics, and inferential is the root word sort of there is inference or infer, and what this means is that we're using our sample data to make some kind of inference about a population, and to do that we need to test some research hypotheses, and that's sort of what this first section of this lecture is about here. So a hypothesis, just by way of review, is nothing more really than a prediction about the relationship between two or more variables. Often those variables are the independent variable or the dependent variable. I'm just going to move myself so that we can see the words. The dependent variable is the thing that we're interested in explaining. It's often the outcome. It's the sort of where we expect a change to occur. The independent variable is often thought of as the intervention. That's the variable that leads to the change in the dependent variable. If you wanted to think of sort of a simple example, an independent variable might be a treatment of some kind, and the dependent variable might be a problem, a mental health condition or a health problem or something like that. So we would expect the treatment to somehow impact the level of that dependent variable. And typically with treatments, we hope that they improve whatever problem it is that we're thinking about. So let me just advance this slide here. So as I said, this is really about inferential statistics, and so what we're doing is we're drawing data from a population of people, and we're using that to test some kind of relationship, some kind of parameter, and then we can generalize that finding back to the population of people from which it was drawn. But in order to do that, well, we sort of need to ask ourselves, to what extent is our sample similar to the population of people from which it was drawn? Another way to phrase that would be, what's the probability that what we find in our sample is actually a true relationship? Which is to say, it actually holds true for the population. And this is sort of where significance testing comes in and where hypothesis testing comes in. So there's a bit of a logic game to this, and let me explain it, and I've got some sort of summary slides here at the end. So if you're feeling a little confused as we go through this, it's okay, because there's these summary slides at a couple of different points. So essentially what we do in hypothesis testing is we state two competing or opposing hypotheses. We then compare our sample data with these hypotheses, and we make a decision regarding a hypothesis, regarding which one we're going to reject. Now, the way this works is you can actually only reject a hypothesis, you can't accept them. But by virtue of rejecting one hypothesis, what that means is that we're sort of embracing or giving favor to the other hypothesis because we had to reject the one. So more on that in a second. So the first thing that we're going to do is we're going to articulate these two competing hypotheses. Typically the first of those two hypotheses that we articulate is the research hypothesis. This is sometimes called the alternative hypothesis. You sometimes see it written out as H1. And so the sort of generic form for the alternative hypothesis is that there's a relationship between some independent variable and the dependent variable. The independent variable will have an effect on the dependent variable. It might have a positive effect or a negative effect or something like that. Here's an example. Let me just move my picture real quick. Participation in our new program will reduce psychiatric hospitalizations. So what we're saying is that there's a relationship between our program and psychiatric hospitalizations. So in this case, the psychiatric hospitalizations are the dependent variable, and the program is the independent variable. The second step here, I'll just move myself down, is to state the null hypothesis. And the null hypothesis doesn't actually It doesn't really have a different name or a synonym, but you sometimes see it abbreviated H0, and in this case, the 0 is sort of the stand-in for null. And the null hypothesis is simply the opposite of the alternative or research hypothesis, and that's that there's no relationship between the two variables that we're studying. Another way of sort of expressing this in terms of the example from the previous slide is that participation in our program is not related to psychiatric hospitalization. So it has no effect, right? Participating in this program has no effect on psychiatric hospitalizations. Just move myself back down here and advance the slide. So again, just real quick, I forgot I put this slide in here. The alternative hypothesis, often denoted as H1 or the research hypothesis. The null hypothesis doesn't really have another synonym, but you sometimes see it abbreviated H0. So third step in hypothesis testing is set some criteria for a decision. And this is effectively asking at what point or what level of risk are we willing to take that our findings are due to chance. And sort of, like I said, all of this will sort of come together in a couple of minutes here. This is often done before we analyze data. And let me just move my picture so we can see all this. The cutoff is often called the alpha level, or the level of significance, and that's simply the probability that the hypothesis is true. So again, as I was saying, the cutoff is often this level of significance, and that's really the probability that the null hypothesis is true. Where do we draw the line? So where do we draw the line? Most of the time we set that p-value, or that alpha level at 0.05. That effectively means what we're willing to tolerate is a 5% chance that our results are due to sheer coincidence. Occasionally you see p-values reduced to 0.01. That simply means that there's a 1%, we're willing to tolerate a 1% chance that our results are due to coincidence. And then increasingly, sometimes we see calls for 0.001, and that simply means that we're willing to tolerate a tenth of 1% chance that our results are due to coincidence. Now, for this class, we only have to worry about significance testing at the p equals 0.05 level. We don't have to worry about any of these other levels. But what you should know is that oftentimes in health services research, we often want a stricter p level, or a lower p level, because that means that there's less of a likelihood that our results are due to chance, and that the effect is actually due to whatever the independent variable it is that we're studying, either a medication or a treatment or a problem of some kind. But typically, I'll just say one other thing. We're when we do post hoc research, which is analyze data after the fact, that significance level is often set at 0.05, which is pretty common. And like I said, that's what you need to worry about for this class. So fourth step in the hypothesis testing process is to collect data and conduct the statistical test. And then when you conduct that statistical test, you'll get a p-value. More on this in a little bit. And that lets you determine whether or not you're going to reject the null hypothesis or fail to reject the null hypothesis. And that's where you make a decision, which is the fifth step. When the p-value of the statistical test that you ran is less than your alpha, we reject the null hypothesis, which means we sort of embrace the research hypothesis. That effectively means that our research hypothesis is the one that we're sort of giving credence or giving credit to. That means there's a relationship between the two variables that we're studying. When the p-value is greater than alpha, so when p is greater than 0.05, we fail to reject the null hypothesis. And what that means is that the null hypothesis is the thing we're rejecting. And remember, the null hypothesis simply says there's no relationship between the variables that we're studying. So in general, when we're doing statistical tests, we sort of want things to be, we want our p-values to be lower than that alpha, whatever that significance criteria that we set beforehand, because that means there's a relationship between the variables that we're studying. So a bit of a recap here. If a relationship is statistically significant, what that means is that the p-value is less than 0.05. That corresponds to an alpha level that we set before we started doing all these statistics, which is sort of that arbitrary criteria or that arbitrary statement that we're willing to tolerate a certain level of chance in our results. So if a relationship is statistically significant, we're willing to say that chance is not really at play here. It's not a plausible rival hypothesis. And what we're sort of saying is that the relationship between these two variables can be generalized beyond our sample back to the population. So hypothesis testing, though, is imperfect. We could make determinations about relationships and determinations about hypotheses, and we could be wrong. There's sort of two ways to be wrong, and the two words for the ways to be wrong are type 1 error and type 2 error. Let me tell you what these are real quick. A type 1 error happens when we reject the null hypothesis when the null hypothesis is actually true, which is to say we conclude that there is a relationship between two variables when in actuality there is no relationship between those two variables. So when we set the alpha level at 0.05, we're essentially saying that there's a 5% risk that we're committing a type 1 error. If we reduce that alpha level from 0.05 to say 0.01, we're reducing the risk of type 1 error. That makes it harder to reject the null hypothesis. This is often a good thing. This is a thing we want to do, especially in like health services research, where we're really trying to find out if an intervention is effective or not. We want to be absolutely certain that our intervention works. So we're willing to sort of raise the bar of our hypothesis tests, and we sort of raise the bar by lowering the alpha. Okay. A type 2 error, on the other hand, is failing to reject the null hypothesis when it's really false. That's essentially concluding that there is no relationship when there is actually a relationship. In health research, we're actually a little bit more willing to tolerate a type 2 error, because if we see no relationship when there is in fact a relationship, what this means is that we're not actually likely to do any harm to anyone or use an intervention that's actually going to cause any harm. The worst case scenario is that it might waste resources or something like that. But typically in health-oriented research, we're more concerned with type 1 errors than we are with type 2 errors. There are ways to protect against type 2 errors. They're sort of beyond the scope of what we need to talk about in this class. Typically people will do that by testing effect sizes and things like that. But like I said, that's sort of beyond the scope of this class. So here's one of these summary slides that I keep talking about. So a p-value, which is also known as an alpha value, is really just a threshold for rejecting or failing to reject the null hypothesis. Another way to say that would be that the p-value is simply the threshold for which we're going to use to determine whether or not there is a relationship between two variables. believe it or not, this whole idea of setting p at 0.05 was something that someone just pulled out of thin air. It was actually a statistician who was working about 75 years ago. He just sort of picked 0.05, and it's something that sort of stuck. Second point I wanted to make here, if we reduce our alpha value, if we make that alpha value smaller, we're guarding against type 1 error. That's a good idea for health-oriented research. Type 2 errors are a little bit more tough, a little bit more difficult to guard against. We use typically effect size calculations. However, most of the time and in most cases, the threshold for determining significance is still this 5% or 0.05 level, because remember, a percentage is nothing more than a decimal, right? And 5% and 0.05 are the same thing. They're just expressed differently. So, where do we go next? Let's talk about selecting statistical tests. How to select statistical tests. So, a couple of things determine which statistical test you're going to use. First is the distribution of variables within the population. The second is the level of measurement of the independent and dependent variables. There are two big categories of tests, parametric tests and non-parametric tests. We'll talk about parametric tests, but we're actually going to use non-parametric tests a little bit more. So in a parametric test, at least one variable, usually the dependent variable, is at the interval or ratio level of measurement. Dependent variable should be normally distributed. Sample should be randomly selected. Typically, you need a large sample. And let me just move my picture here so we can see this last one. And a good sort of heuristic is that if the mean and standard deviation are appropriate descriptive statistics, parametric tests probably are a good idea. A non-parametric test, on the other hand, is typically what we use when we have data at the nominal or ordinal level. The DV does not need to be normally distributed, and we can have a smaller number of respondents. Non-parametric tests are what typically we use in social work research. In fact, on the next slide, we're going to talk about a couple of different tests that I'm only giving you one parametric test. The rest are non-parametric. Okay. So what are the tests that we're going to talk about here? Here they are. They are t-tests, an ANOVA, a Pearson's R, or a correlation, a chi-square. A chi-square is the non-parametric one, and then a regression. And let me put myself up here real quick. This slide, by the way, is sort of what you need to do this week's brief assignment. So you're gonna in the assignment this week, you're gonna tell me which test you would use given data at certain levels. So if you had, for example, a dependent variable that was at the interval or ratio level and an independent variable that was at the nominal level, you would use either a t-test or an ANOVA. If you had a DV that was at the interval level and you had an independent variable that was also at the interval level, you would use a regression. You could also use Pearson's R, so there would be more than one correct answer there. If you had both an independent variable and a dependent variable that were at the nominal level, you could use a chi-square, right? So I'm going to take you through what each of these tests are here in the next couple of slides. But again, this slide, this chart here in particular, is going to be helpful for the assignment for this week. So, what are the different things that these tests do? So a t-test tells us if there is a significant difference between two scores, right? Maybe we want to know if there's a significant difference between a participant score and a sample score. I'll give you an example of that. Maybe we want to know if a participant's SAT score, just as an example, is significantly higher or lower than maybe a sample of people who are in some way similar to what this participant is. Maybe we want to compare scores between two groups of participants. So maybe we want to see if people in treatment group A have a significantly different score on a depression inventory than people in treatment group B. That would be the second bullet point there. And then for the third bullet point, we could look at the difference between pre-test scores of participants and post-test scores. So maybe we have a group of people who are all participating in a group therapy for depression. We could assess their depression at pre-test, we could assess their depression at post-test, and we could ask ourselves or we could ask the data if there's a significant difference between those two scores. And hopefully there is, which would mean that the treatment helped this particular group of people. An ANOVA is very similar to a t-test. The only difference is that it can be used with 3 or more groups of people. So an ANOVA is short for analysis of variance. So the AN in ANOVA is, from the AN of analysis. The O is from the O in of, and then the VA comes from the first 2 letters of the word variance. So analysis of variance. It's just like a t-test, except that there can be 3 or more groups. And I gave you a couple of examples here on the slide. So we might ask, is there a difference between 3 groups of participants, right? So maybe a control group, a group that got, say, treatment 1, and then a group that got treatment 2. By the same token, we could also use an ANOVA if we were asking if participants had different scores at baseline, post-test, and follow-up, right? Maybe we took that same question from the previous slide where we were talking about t-tests, and we simply added a follow-up score or a follow-up assessment. We could ask ourselves if there were significant differences at any of these 3 points. So typically, if you have 2 groups, you're using an ANOVA. If you have 2 groups, you're using a t-test. If you have 3 groups, you're using an ANOVA. Pearson's R. So Pearson's R is named for Carl Pearson, who was a statistician or a mathematician, really, working about 100 years ago. Pearson's R is also known as the correlation. And a correlation essentially tells us if there is a linear relationship between 2 variables. For example, there is a linear relationship between height and weight. There's a linear relationship between income, let's say between years of education and income, right? So just as with height and weight, as one increases, so does the other. Same thing, the same kind of relationship exists between years of education and income. Typically, the more years of education a person has, the higher their income is. Those are examples of positive correlations. There are certainly examples of negative correlations as well, and that simply means that the linear relationship is negative. Okay, so chi-square is the only non-parametric test that we're talking about here. And a chi-square tells us if there's a relationship between basically categorical variables. We can use them for ordinal variables as too. So think about any 2 categorical or ordinal variables and ask yourself if you'd want to know if there was a relationship between those. I came up with a couple of examples here. The first one is a little silly. But maybe we'd want to know this. Maybe we'd be curious to see if there was a relationship between hair color and religious preference. My guess would be there isn't, right? But both of those are categorical variables, right? We can't put them in any kind of order. We can't say that one's better than the other. But there's often times where we want to look at relationship between categorical variables. So we could use income and education, right? We couldn't think of these as interval or ratio levels, but we can think of income and education as categorical or ordinal variables, and we could look at the relationship between those. We also could think about diagnosis and type of treatment as categorical variables, right? So diagnosis could be yes or no. Type of treatment could be treatment 1 or treatment 2, or it could be treatment and control. We could look for a relationship between those kinds of categorical variables. And then a regression tells us if a change in the independent variable is associated with a change in the dependent variable. So I'll give you a couple examples here. Let me just move my picture here. So we might ask if an increase in income is associated with an increase in job satisfaction. Probably is. We might ask if an increase in treatment attendance is associated with an increase in symptom improvement. Probably is. We might ask if an increase in education level is associated with an increase in income. It probably is. There's probably 1,000 examples that we could think about with regression. The ones that I listed here were all sort of positive regressions, right? Just like in correlation, where an increase in one is associated with an increase in other. But there are certainly times when an increase in one variable could be associated with a decrease in another variable. I'll give you an example. So oftentimes in my research, what I see is that an increase in say, alcohol use or alcohol dependence is associated with a decrease in, say, the quality of a relationship or a person's performance at work. So an increase in their symptom level is essentially associated with a decrease in, a quality of life or an activity of daily living function. Right. So when we're looking at those kinds of variables, again, we typically think about using a regression. So what does all this have to do with p-values? When you run, so this is another slide where I'm sort of attempting to bring it all together for you. Okay? When you run any of these statistical tests, we will also get a p-value. And that essentially is what tells us whether or not our results are statistically significant. So how do we determine if something is statistically significant? Well, typically it's that p-value is less than 0.05, or whatever it is we set our alpha value at. But remember, like I said a minute ago, we're going to use 0.05 as our significance criteria. What happens if p equals 0.05? Guess what? It's not significant. So that's what I mean by the last bullet point that you see on the slide there. It's not statistically significant if p is greater than or equal to 0.05. So 0.049, you're in good shape. 0.05, not statistically significant. Let me advance the slide here. So what does this mean? Let me just move myself down here a little bit. So if something is statistically significant, that lets you reject the null hypothesis and essentially embrace your research hypothesis and conclude that there is likely a relationship between the two variables that you're studying. If it is not statistically significant, what this means is that you fail to reject your null hypothesis and there is no relationship between the two variables that you're studying. Often, we want to see statistically significant results, right? Because typically that means a treatment is working or there's a relationship between these two variables. But there's lots of times when we are really happy when things are not statistically significant, right? For example, we might be really happy to know that exposure to certain chemicals are not associated with cancer, right? That would be great news, and that would be a time when we'd be really happy to not see statistically significant results. We probably would be disappointed if a treatment did not improve a dependent variable. We'd probably be disappointed then if we didn't see statistically significant results. But don't confuse statistically significant with important and meaningful. There are lots of times when we can see no relationship between variables and be really happy that there's no relationship between two variables. So statistically significant does not mean meaningful. It simply means statistically significant. It's up to the researcher, it's up to the expert to determine whether or not results are meaningful. Okay? So So to be a little bit more technical about this, and this is sort of the last couple of slides here of the presentation. But statistical significance testing is essentially a quantification of the confidence that results are due to chance. So if I run a statistical test, this happens all the time, I get a p-value of 0.001, 0.001. What I can say is that there is 0.1% chance that my results are due to coincidence. That's good. I can be pretty darn confident that the results I'm seeing are because there is actually a true relationship between the two variables that I'm studying. However, this happened to me the other day. I ran a statistical test. I saw that p was equal to 0.889. That essentially means there is an 88.9% chance that coincidence, that happenstance, explains the relationship between those two variables, right? Essentially means there's no relationship between those two variables. Happens all the time, okay? So this essentially is a decision criterion for us, okay? So what does all this have to do with the normal curve? Well, p-values and z-scores are actually very similar in their nature. If you remember from a couple of weeks ago, a z-score is essentially tells us how far away from the mean a score is. And a p-value essentially does the same thing. A p-value tells us where on this range of possible results our findings fall. And just as a z-score that's really high is very unlikely to happen, a p-value that's really small simply means that there's a low likelihood that these results are occurring due to chance. So this is not something I think you need to know for the exam. It sort of is my attempt to bring together the information from a couple of weeks ago with this information. P-value calculations are all based on the normal curve or the Bell distribution that we talked about a couple of weeks ago. And so that's why we talked about it a couple of weeks ago, and that's sort of how all this information goes together. So p-values that are really, really small are essentially saying that those results are occurring way out here, right? Where infrequent, way out at the tails of the normal curve or the Bell curve, where there's a really low likelihood that these of these scores occurring. So that's how they sort of relate. At any rate, I don't think you need to know that for this information, the task for this week. What we're going to be talking about in the discussion is the assignment for this week. You're going to be picking the statistical test based on the criteria that I'm giving you. I would again go back to the chart that's earlier in this presentation and use that as your guide for selecting the right statistical test. And then next week what we're going to do is we're going to practice a couple of these in Excel. Thanks for watching. As always, you have questions, get in touch with me. All right, thanks very much.